Welcome to another unit in this workbook statistics, this time focusing on the so-called uniform distribution. The best idea to think about a uniform distribution is by starting with its discrete version, because there it's more or less like throwing a dice. If you have a normal dice, each of the sides has the same probability of, being rolled. So if we have a six-sided dice, each side has a probability of 1 in 6 to get rolled. And that's actually the main idea behind the uniform distribution. Each result has the same probability of occurrence. However, we can talk about the uniform distribution, which then usually is called the rectangular distribution, in a discrete context or in a continuous context. And that's actually the one I want to focus on here, the uniform distribution in a continuous context. So we have an interval from A to B, and any value in the interval can happen at the same probability. In this case, we get a density function, which is more or less just a flat line, and it goes from A to B and has the height of 1 divided by B minus A, which is nothing else than the length of the interval. In the other part, this density function is 0. The big advantage of having such an easy density function is we can very easily also calculate the distribution function, which then looks like this. Starts at 0, ends at 1, and between this, for the same interval from A to B, it has this form for a certain value x. Keeping this in the back of our mind, we can return to the density function and take a look how this will look like graphically. Here we see we have this interval at this point from 4 to 8, and in this interval we have a value which is just 1 divided by the width of the interval. The interval has a width of 4, so 1/4 is the height of this density function at those points. Outside of the interval, the density function has values of 0, so that the area below the density function is exactly 1 or 100%. With those comments on the density function, we then can continue with calculating probabilities, and that's just an application of our distribution function, which we, in one way motivated on the slide before. So here, the probability of having, for example, to wait less than k minutes, or that result will be less than a value of k, means we simply insert k for the x from the distribution function from the slide before, with the comment that k needs to be within the interval A to B. I mentioned in the earlier comment, this could be, for example, waiting times. So if you arrive at a train station, you don't know when the next train arrives, but you know that the train always comes every 20 minutes. Then you have an A, let's say of 0, and a B of 20, and you can calculate any probability of how long you will have to wait. For example, what's the probability of having to wait less than 10 minutes? Then the k would be 10, but the k can only take values between 0 and 20, because the latest you have to wait is 20 minutes. The shortest you have to wait would be 0 minutes. The train already is there. So that's what this comment with the k has to be somewhere in the interval actually means. The big advantage, if we know that's the probability, we can also use this to easily calculate the probability of our result or random variable being somewhere in an area from k1 to k2. Because here we would first insert k2 and then minus and then k1 inserted. However, we have two fractions which we subtract from each other with the same denominator. So we can put them together into one fraction, which then would look like this. So that's actually pretty neat, because this simplifies the calculation of these, in other ways, usually more complex probabilities. Finally, we can also define our two central statistics, which are the mean or the expected value and the variance, and thereby also the standard deviation. Here it's relatively easy. Well, since the density function is just a flat line, the mean is the value in the middle. So just a plus b divided by 2, which is just the value here in the middle. Variance might be a bit harder to be explained, but it's more or less similar from the underlying idea. Well, in either case, those are the two statistics for any variable following a uniform distribution. Well, with this also our unit on the uniform distribution ends. I hope you enjoyed it. I say goodbye and see you next time.